following video is on limits with graphs. Remember the notation from the previous video. If f of x gets closer and closer to L as x gets closer and closer to C from above and below, then we write the limit as x goes to C of f of x equals L. If f of x approaches L from below C, we write the limit as x goes to C with a superscript negative sign of f of x equals L. If f of x approaches L from above C, we write the limit as x goes to C with a superscript plus sign of f of x equals L. So in the following diagram, we have a function, which we're going to call f of x. And let's start by trying to find f of 1. Remember that f of 1 means that we start at x equals 1 and we trace it up until we find the solid dot, which in this case occurs at y equals 2. So f of 1 equals 2. Now let's try to find the limit as x goes to 1 from below of f of x. We don't know what this function is exactly, so we can't plug in values close to 1. But we can use the x-axis and the graph to find values of x that are relatively close to 1. We trace it up from the x value until we hit the curve, and then we see what the y value is at that point. We can do this as we get closer and closer to 1, and we see that the y value is getting closer and closer to 2. So, the limit as x goes to 1 from below of f of x is 2. We can do the same thing for the limit as x goes to 1 from above f of x. We choose values close to 1, but slightly bigger than 1. We trace up until we hit the curve, and then we see what the y value is at that point. We can keep doing this as we get closer and closer to 1, and in this case we see that the y value is getting closer and closer to 4. So the limit as x goes to 1 from above of f of x is 4. Since the two limits from above and below disagree, we say that the limit as x goes to 1 of f of x does not exist. Remember, with limits, it does not matter what happens at the point. It only matters what happens as we get very, very close to the point. So let's look at the following three values on this graph. Let's look at x equals -1, x equals 1, and x equals 3. Starting with -1, let's try to find f of -1. We look at x equals -1 and we trace up until we hit a solid point, which seems to happen when y is equal to 3. So f of -1 is 3. Now let's find the limit as x goes to -1 from below of f of x. So we're going to choose values of x that are slightly less than -1, and we're going to trace them up until we hit the curve and see what we're getting closer to. Notice in this case the y value is getting closer and closer to +1. So the limit as x goes to -1 from below is 1. We can do the same thing for the limit as x goes to -1 from above. Once again, we trace up from a value slightly bigger than -1 until we hit the curve, then we trace over to find the y value, and again this seems to be getting closer and closer to 1. Since the limits from above and below both go to 1, the limit as x goes to -1 of f of x is 1. Now let's try f of 1. Notice that if we trace up or down until we hit the curve, we're only ever going to see the open dot. Open dots mean that the function is not defined at that point. So, f of 1 does not exist. We can, however, try to evaluate the limit as x goes to 1 from below. So if I choose a value slightly less than 1 and trace it until I hit the curve, I seem to get a value that's very close to -3. So the limit as x goes to 1 from below of f of x is -3. If I try to estimate the limit as x goes to 1 from above of f of x, I choose a value of x that's slightly greater than 1, trace it down until I hit the curve, and then look at the y value there. And once again, this seems to be getting closer to -3. So since the limit from above 1 and below 1 both go to -3, the limit as x goes to 1 itself of f of x is -3. Finally, let's look at f of 3. f of 3 has a solid dot when y equals 4, so f of 3 equals 4. The limit as x goes to 3 from below of f of x can be found by choosing any value less than 3, tracing it up until we hit the curve, and if you do this on your own, you'll notice that it seems to be going to +4. Once again, if we try to find the limit as x goes to 3 from above of f of x, I can choose any x value slightly bigger than 3, trace it up until I hit the curve, and again, I'm going to expect in this case that it goes to 4. Since the limits from above and below 3 both go to 4, the limit as x goes to 3 of f of x is 4. Remember, it doesn't matter what happens at x equals c, it only matters what happens as x gets close to c when we're taking a limit. There's 3 ways that a limit can fail to exist. We've already discussed the first way, and that is when a limit as x goes to c from below does not agree with the limit as x goes to c from above. The second way is when the limit as x goes to c from either above or below are infinite. And the third is when the function oscillates wildly as x gets closer to c. The first type is shown in the picture on the far left down below. The picture calls it a discontinuity, but I would rather call it a jump. It's a specific type of discontinuity. So notice that as we approach from above and below c, the y values differ. In the second picture in the middle, the image calls it blowing up. I like to think of it as the y value is going to positive or negative infinity. And the third way a limit can fail to exist is if the function is oscillating wildly. Notice that if we get closer and closer to the dotted line, it's hard to tell what the y value is because the function is going up and down so fast. Let's look at some examples of oscillations. So the limit as x goes to 0 of sine of 1 over x. The graph looks something like this, and notice that as x gets closer and closer to 0, the y value is hard to determine because the function is going up and down so quickly. So we write that the limit as x goes to 0 of sine of 1 over x does not exist. Notice that not all oscillations are bad. The limit as x goes to 0 of sine of x over x looks like the following function. And notice here that as x goes to 0, y goes to 1. And that happens on both sides. If we approach 0 from above and below, the y value is going to 1. So in this case, the limit as x goes to 0 of sine x over x equals 1. So not all oscillations are bad, only when it oscillates so fast that we can't tell what the y value is.